Okay, so would you guide us to download the NNA tool?
Absolutely.
Finally?
Correct. I leave a link on our chatting windows, so you guys can download it. For those who couldn't see the chatting, actually I can see the link. This is our main page, right? So I'm going to go down, all the way down here. There's a tool. So there's the link. Simply click it and it drives you to a Dropbox link here. So I guess you can just download. I don't know why I can see this is Korean, but I don't know. You can download from this, the G file. Let's say Dropbox here. Yeah, it should be download the link. Yeah. And once you download it and unzip it, right?
If you have any problem, just bring up your issue here on chat or just the voice. It's
Right.
okay.
So once you unzip, you can see two folders here. So one is the add-on, the other one is the example. The first one, we need to install the add-on correctly. So this is very simple, right? So let's jump to Rhino here. So I just opened the one Grasshopper here, and then go to File and Special Folders, and then Component folder. Again, File, Special Folders, Component folder in Grasshopper pull-down menu. Once you click it, you can see a library folder here. So what you need to do is simply copy these two files to that directory, the library directory here. Once you successfully copy the file to library's directory, then you must restart Rhino again. Yeah. And then restart Rhino and Grasshopper here. We can see new menu called the NNA tab here. So if you click it, you can see all menus. Some of them is still under the construction, but most of them is working correctly right now. Once you figure it out, you can see this NNA tool on the menu here in Grasshopper. Then let's try to open one of the example. Here, example file folder, sorry. And we have two folders inside of the example folder. We're gonna start from basic here. And then I'm going to drag one of the, not one of them, the first example on top of the Grasshopper interface here, canvas, let's say. I just release my mouse. Okay. Give it some time.
Maybe I think it would be better to wait just like 1 minute for everyone get ready.
Sure.
Probably.
Yeah.
They may have some troubles.
Yeah.
Yeah, downloading and installing.
Sure. Please raise hand if you got problem or any question related to installing NNA tool to your Grasshopper add-on. Great. We have one. I have a problem. I cannot see menu yet. Did you restart after installation?
You have to close your Grasshopper and Rhino and.
Then my question is, did you copy the file to the right folder? The right folder is special folder and component folder. Yeah. Really? That's weird. Component folder, you can, okay. Oh, I see. I think you have lower version of Rhino and Grasshopper, I think. Could you please try to, yeah, but Rhino 6, but
Maybe yeah, SR.
yeah, Rhino 6 has a different version. So we basically develop on the, not like latest version, but I think I would like to check like the Grasshopper version. So I use the build version 100007 things.
Can you update your Rhino?
Yeah, I think NJ&Woo has the same problem, and then once you updated the Rhino and Grasshopper is automatically update, then all the SDK and all the API gonna be up to date. And any other problem? Can you leave any message in case that you successfully install and open open the example file?
Yeah, somebody makes success.
Okay.
Or can you share your screen? Like somebody,
Yeah,
if you have an issue,
yeah,
maybe you can share your screen and we can see.
Yes, so my Rhino version is Rhino 6 SR26. Oh, okay. Oh yeah, I think this is the one thing that you can try. So what she or he?
Oh, okay.
So
Kim Dong-gyun works well.
great news. We have one person. Okay, bear with us. We're gonna solve this problem. No worries. Don't panic. We can make it.
Carlos is working well.
Great.
Okay.
So maybe you can click the right button on top of network analysis.gha and then properties here. There's a, for some people, you guys can face like unblock whatever things. Just check it just in case. Yeah, I think so. I think I'm on the right track. Yeah. And then I think we can, because we're gonna record this video anyhow, so we can start the workshop. And then at the end of the workshop, after workshop, I basically, can individually visit you guys' computer and can see what's going on behind the scene. Then we can fix it. Okay.
Yeah, I think some of you working well. So we just start again our workshop. If it doesn't work right now, just leave it and just watch the lecture first, and then you can try it later, and we definitely help you out, and we have extra kind of prep session, so don't worry about it.
Sounds great.
Yeah, I will start.
Yes, please.
I thought it could be good to show you kind of one example project, kind of real project, which the research site was in Cambridge. But I think it's better. I show you maybe later, maybe in the second maybe lecture. I will show you this project. I will share the project. So before jumping into the workshop, I will quickly explain our numeric network analysis toolbox for Rhino Grasshopper. So this is the utility overview diagram. So we provide these kind of services and utility functions on this NNA toolbox. So today we're gonna focus on the centrality and accessibility. We learn about a lot of like theories and concepts today. So we have to observe, like kind of digest by doing some kind of short exercise or like workshop. So we're gonna focus on two theories and play with our NNA toolbox. But it's very straightforward, very simple way. So because I just to show you some kind of basic things, so I'm pretty sure you can follow smoothly. So our NNA toolbox offers kind of very easy approach for measuring distance and analyzing various accessibility and hierarchical issues. And we really wanna use this tool for designers, like urban designers, and of course for the advanced version, maybe urban planners or urban researchers or marketing analysts can use this tool as well. And this is very fast-paced analysis. It's really possible, so it's kind of good to accelerate your design thinking process and decision making process. So hopefully this tool really help out many designers and also architects as well. So this is when you open your NNA, when you download it, and then when you open your Grasshopper, you can see this user interface shapes, right? So it really looks like that. So with me, I will just focus on this basic analysis, and after me, the NJ will guide how to use the custom network analysis part. So here, the first set of tool, this is about the network setup utility part, so which really help out clean the lines and build a new network data set in Grasshopper. So I already clean up all the data and I collect NJ, and we collected all the urban data from Cambridge and Manhattan and Seoul. But the problem was that there is some kind of road network lines wasn't really clean, and we have to clean out everything, you know, to operate better and more effectively or efficiently. So and then we talk a lot how to solve out this issue. So we developed this network utility part. So it simply clean up your line data to ready for your next step, which is a network analysis. So for the network analysis part, we have two different versions, as I said. Like first one is a basic analysis. It's very very straightforward. So if you wanna just a quick exercise for your site and for your understanding about the urban context, you just use this. And if you know about the coding and C# or Python, you can develop further, or you can achieve more in-depth analysis, spatial analysis by using this part. So after this workshop, also we have a prep section as well, like tomorrow and after the second lecture as well. So maybe we can show kind of some more examples how to use the custom network tools. And of course, we will get lots of data after the network analysis, right? It's to be like huge data. Like for example, if you input like origin data, like as many as you want, like let's say like more than like 300 origins or like 1,000 origins, I tested and still working, okay? But once you calculated all this kind of origin data, you will get the big chunk of like big urban data results. So usually you have to bring this big data to the statistic tool like such as like R or like Stata or RStudio, and you have to use a statistical tool to understand what is the meaning of the data result. But we developed this data part, so you can very quickly check your data descriptions, like what is medium and what is the mean, or what is the mean max, and what is the standard deviation, and so on. So or you can check, you can draw the histogram or scatter plot, and or even you can draw the fit line, regression line, and you can check the correlations between two results. So it's kind of very helpful to check out your urban data results by using these applications. And this last chapter, we are still working on that. Hopefully, we can develop further after this, or throughout this workshop session. Because this is like more agent-based network analysis, which is very advanced version, and also artistic as well. So hopefully, we can play with some examples with you and develop with your ideas as well. So this is a kind of brief introduction about the tool. So let's move on to the examples. I will just the first example is about the centrality test. We studied a lot about what is the centrality today, right? The key thing is to understand the hierarchy of the context in the spatial network, right? You have to remember this. And yeah, let's move on to grasshopper. So here, exercise 1, we study about the hierarchy context in Manhattan area. So here is the, you can see the NNA toolbox. So here, I already embedded the road network in this component. So when you click it, you can read the data. Like here, you can see in this component, there is like 1,400 the curves in this file. So to clean up or to make working in our network analysis, so we just connect with the split polylines to lines. So this is here. So you just simply link with this, and it's already ready to reset up the road network to evaluate our centrality analysis. So you just link it, simply just link it to the lines here. And here is the rebuild, the concept, which is you can pause and you can run, you can decide, because it's kind of heavy data, because we try to show you kind of medium size of urban context. Of course, it could be a like regional scale, much bigger scale than this. We just decide like kind of medium scale of it, which means like larger than neighborhood scale but smaller than the regional scale. So it's pretty much a heavy data scale. So if it just run once, actually it takes quite a long time. So once you can click, you can control it, like when you wanna run this the component or not. So here the origin data is a street cafe, which is located around here. And then destination can be the 4 squares. So I want to show you the whole context of Manhattan here. So if you just click it, it is the zip area, the data here. So our research site is like here. So here's the Midtown area. Here is the Central Park. I believe that you guys are familiar with the Manhattan context, right? So here is the Manhattan, here is the Midtown. So we just focus on the four squares, which is Union, Madison, and what is that? Harvard and the Times Square. So we focus on this area for these exercises. So let's move it. So we decide the origin with the street cafe and destination is 4th Street. So what we want to learn about is that how central value for the four squares. So this component help out evaluate the network. And then this is a closeness component you can find here. You can open, when you open this component, we just named very straightforward way, right? It's a network analysis. Gravity, half, reach, betweenness, closeness, then degree, straightness. Very straightforward. So you just bring one of them. So these four is about the centrality analysis, and those three is for accessibility analysis, right? And network analysis is helping out to do this method. So here we're gonna do the closeness analysis here, because we wanna learn about how close between origins and destinations. We just wanna see the relationship, like how close they are. So here is a closeness component, and it's very straightforward, right? We really carefully define the name as well. So here is NS and here is NS. And offset is control the size of visualization. So here's one question. If you have a question, like just jump in and ask us. And then the offset control the visualization size, and this is it's about the ID, which means that actually the all origin has its own IDs. Like let's look at it. Like how many points in here? So it has a 121 points. So it means that, but the grasshopper count from 0, so which means that it has a 120 ID in this component. You got the point, right? So the each ID represents the each locations of origins. So here we have a 121 origins, and here we will have 120 IDs. So this ID component really control, you can select specific ID or specific origin locations, one of them, and then you can check individually. But if you don't connect with anything else, it just the default value is -1. So -1 means that it just describe all the data. So let's look at it here. Maybe it's too small. The visualization, this dot line is, if it is too small, maybe we can change the size of the offset. Like, okay, here, let's say 200, and commit change, and let's see how it changed the size of the dot, the circle. Yeah, it's getting bigger, right? So, okay. Yeah. And this is a mesh. So M is a mesh, and NS is like all the network data is in here. So, and then PL means the showing the shortest path, linking between all destinations and all origins. So this is the path between origin and destinations. And this is the text data, which means the closeness. We are doing the closeness analysis, right? So this data showing about the closeness index. So let's move it here. I explain you the warm color, the red color means the higher value, and cold color is if it is close to blue is the lower value. So we can see like here the okay, let's move here. The warm color, the orange is around like 5,000 value, and but the cooler color like light green is like 4,500. The closeness index. So this is lower than this. So this is like overall understanding about the closeness context. So we can interpret this result, right? Or if somebody can interpret this result, it or maybe I can interpret it for you. So closeness is which we talk about like lower value means that more close each other, right? So this is actually quite makes sense because if we indicate like all the origins here, like so around here it like has a very cold color, which means the very low value, right? But for the closeness analysis, the lower value means the more closer relationship between origin and destination. So which is makes sense, right? Our destination is like here, around here, here, here. So yeah, this some kind of origins were located in the middle of the site. It should be more closer relationship with all destinations. So we can kind of clearly verify this closeness concept with our NNA tool. So let's move on to the betweenness. So betweenness, you guys have a very lot of questions about the concept, right? So hopefully you can understand the concept using this tool. So here the result is the progress is same. You just generate the network and just simply link with this second. The here the text represents the result of closeness index. So this text represents about the index value after the closeness analysis. Okay. And this is actually the betweenness analysis really reflect the realistic pedestrian flows to destinations. So the progress is same, the operation is same. So if there is no connection with ID, is the default set is -1. So it means that it will show everything. So the result is showing like this. If you want to increase the size of visualization, you can increase the number here. And this show the path between the destinations and origins. And this value, the first value shows the betweenness index value. So if you zoom in, like index value, this one is between 0 to 1, so it's 0 point something something. But we also add one more option here, as you can see here. So this one actually showing the real footfall, which is like number of digits on this edge. So for example, this data doesn't really reflect the color, this between this and this edge. You got it? Yeah. So, so as you can see, actually there's some kind of relationship, right? So between these reflect the realistic pedestrian flows. So as you can see here, this edge is like it's red, means a very high kind of between its value index. But here, if you see the number of digits on this edge is very high compared with other edges, right? So I think you can use the both data. The first one is about between its index value, but the second one here, the out P and out N, is just literally very direct the number of digits on each edge. So, and this is a little bit advanced. I will just quickly explain the concept of this, and then maybe later during our prep workshop session, maybe I can explain more details about it. Or NJ, can you explain this Python component? This one is we just literally wanna check the one-to-one relationship, which is a core relationship between the dollar per square meter feet, which is a real estate value of the real estate value of this street cafe. We get the real estate value, and then we simply compare with the result of the closeness index. So yeah, NJ can explain the.
Actually, I request the.
Oh, really?
You.
Oh, okay. I will.
Can I control your mouse? Yeah.
Oh, yeah.
I think I can hijack. So the question we have right now is very slow, by the way. The question we have right now is we have the betweenness and closeness, right? And then the topological context is exactly the same, but the way of calculating on that network is different, right? We use the betweenness and closeness right now, and then we wanted to see the correlationship between two data. So I think I did nothing special. Here, as you can see, we just bring the result of closeness to the x-axis, which is the linear regression component. And then also we have the pedestrian flow. Is it betweenness, right?
Yeah, it's a betweenness, but this one is we capture the real estate data and then compare between this.
Yeah. And then what I wanted to do is map the individual point is the real estate value, right? So this is the actually Python coding stuff. So let me quickly describe what I did. So I declare a sort of function. So what it does is it found the point, because this is the basically list, and then we get this list and then apply the value along the z-axis. Right now we only use x and y, right? There's no elevation dimension, so I'm just take advantage of the extra dimension. So I remapped all the information as a z-axis, okay? And then we have the the origin points, right? And then I check the distance between individual origin into this particular points, which represents the real estate value, okay? And then I map this real estate value for individual origin. Yeah. So Can you, Jonghyun, can you, I think we need to execute this.
Oh, okay. Yeah, sure.
Yeah. So basically, on the higher level, we have an origin point, and we wanted to map the real estate value for individual origin. Some is like very high, some is very low, right? So I think this is what I wanted to try to say. It's nothing special. And then once you evaluate the network, and then you can see the result in terms of the relationship between two values.
Right. So here the research question is how if the distance between origin and destinations is, if the distance is closer, is it really impact on the real estate value? For example, like here the data is the street cafe to squares, right? So it means that if there is a very, in terms of distance, if it has a very closer relationship, maybe the closer cafe will have a better kind of sales, right? Better margin and better benefit, take advantage from the distance, right? Because there will be a lot of visitors in the squares. So if they want to have like coffee, they will find the kind of like closer cafe nearby the squares. So we assume that this closer cafe should be like more valuable than the further location cafe. So we assume that how those real estate and also real estate value can reflect the value of the cafe as well. So we try to see this closer distance relationship, how could be reflect on the market, the retail market. So maybe it sounds too complicated at this moment. I don't know, like how familiar for you guys. You are designers, but just simply think about like your daily life. Like I visit a park and I want to have a coffee, but I prefer go to closer one, right? So closer a cafe will earn more margin, right? So that area, that cafe will be very popular, and maybe at the same time the real estate value will increase as well, because this cafe can sell lots of products, so it has a very profitable kind of location. So the real estate value will increase together. So we want to see this kind of distance issue and the real estate the value issue together, and then we just see the one-to-one relationship. How those are, is there really the popular cafe has a closer cafe has a more value in terms of real estate? That is the question about this analysis. So when we draw this component also you can find here in data. So it's a regression line which is showing the fit line between two, which you can simply calculate the correlationships between two things. But the data lists should be fit each other. So after that, we calculated the coefficient indicate like 0.775. Actually, it's very good number, because if it is a lower than 0.1, it's very low. So it means that there is no relationship between two. There is no correlationship between two. But if it's over 0.6, it's middle, it's good, or could be good or could be bad. But it's over 0.8, it's very strong. So actually it's almost 80%, so 0.8. So it means better than middle, but slightly less than strong, but it's still very strong relationship. So our research question here is is there really a close relationship between real estate value and closeness between the squares and street cafe? It can say yes, it's a strong relationship between two. So actually, even though it's very basic analysis, you can interpret it, or you can have if you have a kind of very simple urban questions, or you can simply test it by using this analysis tool. Hopefully it's not too complicated for you guys.
I just want to confirm, like, is it so that we're trying to analyze the distance between all the points to the cafe, and the closer they are to the cafe, the real estate value, it increases with the closeness. Is this what we're trying to prove with this?
Yeah, I just actually maybe the internet isn't really stable. I cannot really hear your voice clearly, but yeah, just the cap the research question is about the what is the relationship between real estate value of street cafe and the closeness index between a street cafe and squares, because as you know, in Manhattan, particularly these four squares, it's so popular kind of touristic destinations. You know, like it's always a lot of people are gathering there. So our assumption is the very close is a good closeness will have a good relationship with the real estate value of the street cafe. You can get it?
Yeah.
So if
Thank you.
the cafe is closer to the scare context, the cafe real estate value will high as well. That is the research question and research assumption and hypothesis, and we just exercise with this tool.
Jonghyun, and also we have the other question on the chatting windows.
Oh, yeah, sure.
I think we already counted, right?
Yeah. We already calculated more than one tourist spot. This analysis calculated the multiple destinations and multiple origins. So it already counted the multiple tourist spots as well. Yeah. Even though it's very basic component, actually you can play with or you can test with lots of urban questions actually. So we hopefully, if we have time, we can do kind of more brainstorming. Like if you bring up your research question, maybe I can answer like me and NJ can answer about, okay, you use this component, and then you can play with this and that. And so if you have any kind of urban the questions, just keep it and then share with us, and then we can also guide you like which component is the best can answer for your research questions. So collect all your questions. Or maybe we cannot answer everything, but we try to do our best and try to build your and develop your own questions with our tool. Yeah, this is another centrality test. So this one is a kind of same logic. You know, like we define the network, and the origin is same, the street cafe, and then the destination is 4 squares. And here, this is the straightness. So straightness use the Euclidean distance and network distance. So it's the larger number means the better, like which means the more efficient network condition. So the result showing that here. So here the straightness is a higher value is better, right? So the warm color network. The warm color means the better straightness. So it's more directly linked between origin and destinations. And you can check the result of straightness index here. And here I wanna showing about this data description part. So by using the bin, you can find here in our data part, and then you can draw the kind of this histogram as well. So what I want to show you here is that actually we can play with this as well. So this is the strain is the same, the two strain list analysis, but the destination is the same, the four squares, but the origin is different. The first one origin is a street cafe, but the second origin is about the library and cultural facilities. So we can simply compare with which strain list is better than the other. So the result is showing that okay, so the cafe is like this, but the cultural facilities is like this. So here it looks like more kind of red and orange, and like warm color really occupied more or less all the locations. So it means pretty much good Chinese condition, right? Where than this street cafe, because here for the street cafe here is a still very cold color, and here so the straightness is not really good in this location. So why is it? Maybe we can just simply check here. Yeah, it's kind of far away from the destinations. And let's look at the culture distance. Yeah, probably in terms of location, maybe they are like more evenly distributed, and it's well located near the destinations. So so let's try to understand by using this histogram graph, and also this one is the data description component, which you can find here, data describe. So here you can find the mean, max, mean, median value. And from here, what we can understand is that actually this histogram showing the more kind of left skewed kind of shape. So let's look at here. But so which means that actually more overallly from small number to large number is overally distributed well. But in this case, like the large values, like all kind of many kind of values are occupied in a large value position. So
Yeah,
let's
also
look at it.
you can zoom in the legend. Yeah, and then also legend.
Oh, yeah.
Shows median and band, median and mean value. I mean the
Right.
legend on the Rhino screen.
Yeah, sure. So so let's look at here, like when we check here, so the higher higher value, which is a warm color, is pretty much occupied everywhere. So this one result is really reflect well with this histogram diagram. So if you want to quickly understand the result of your analysis, you can use the bin or data describe. So you check the mean, max, mean value, and variations, standard deviations. You can check it and how those results values they are evenly distributed, or like they just skewed, and just the larger values are more occupied in this result. And you can also check it. Also, we have a very nice legend here in Rhino. So you can also directly see here. Of course, you can use this component as well. But in this gradient color, showing what is the mean, max, visually it's very straightforward. So you can also understand the data results very quickly, even on the Rhino window as well. So we end up the first exercise. Wow, it takes longer than what I expected.
So you can go without break.
Yeah. So I will just go very quickly, like, and maybe if you have maybe you pretty much understand each concept, and I will just very quickly showing the result of the analysis. So the exercise 3 is about the accessibility analysis. So here we understand the, of course, link with the network, build the network analysis here, and then link with the reach analysis. So as I explained, the reach analysis simply captured the counted the number of accessible destinations from origin. So this mesh, yeah, it's still false. So I have to make true to run this component. This now is working. So still the origin is the 4 squares and the destination is a street cafe now. So here is the result. So how many so street cafes can we find on these 4 squares? So here the reach analysis showing that in street cafe we have a 121 cafes, right? So this 121 cafes are distributed on 4 squares. So 10 can be accessible from this square, like which is Times Square, and 10 another 10 can be accessible here, and 30 street cafes can be accessible from here, and 28 cafes are accessible from here. So actually, you can change the reachable the radius. So this unit is feet, is not meter. So don't be confused about this. So if you define I will just keep the minimum distance as a 0. But if you control or change the distance of the walkable distance by using this, of course the reach accessible the number of cafes will increase for each squares, right? If you just decrease. So, and also here the color represents the distance. So it's a network distance. So don't be confused about this. So if you can keep the longer walking distance range, of course, the accessible number of accessible street cafe will increase as well. But this is a simply count by distance, network distance. But we explained about the gravity concept, right? It is the gravity concept is same as reach analysis, but it is discounted by the decay value, which is it could be 0.001 or 0.002, and in terms of the urban context, it can be diverse, right? So let's compare with this reach analysis. So we can just set the same condition. So I will define the max distance is 6,000 here, and here I will say 6,000 as well. So it's the same context, but only the different thing is that the gravity analysis apply the beta value, which is the decay. So this amount of decay value will discount total accessible number of street cafe. So as a result, here, from the reach analysis, the accessible cafe number is like this: 53, 76, 92, 93. But on the reach, on the gravity, as you hear, it dropped dramatically, right? Only one person, one cafe can accessible here, and here is 1.7, and here is a 6 point around 5, and here is almost 6. So the number of accessible cafe is discounted a lot by this beta value. And here, in the gravity analysis, this color represents the gravity value. So this one is not about the distance, it's about the gravity. So in the blue color zone, it means that people can, the cafe cannot access if it's located here. So yeah. This is about the accessibility analysis. So let's move on to the exercise 4. Yeah, this is very fun part, which is about the hop. So we can see the probability. So if we have many options, and if I stand on the Union Square, so which cafe I wanna choose. So let's run. And hop model really demanding kind of lots of calculations. So, we kind of recommend that try to use this inspection point rather than use this ID. If the default number of IDs -1 means that all possibilities will calculate it for this probability analysis. So it demands a lot of kind of energy. So we recommend to use the inspection points and to analysis a specific location for your Hoff model. So let's see the okay. So here is the, so let's move this point, inspection points to the, okay, Union Square. So from here, you can, I will turn on the this text component. So as you can see here from Union Square, you can access. Oh, it's a different way around. Okay, the origin is the street cafe and destination is the 4 squares. So I will just convert, change it, like change the question. So how, from if you are in a cafe, which squares you can access, which squares you want to visit. So that is our research question. So if you are here in this cafe, there is a probability like around 88%. You can, you will travel, you will decide to go Union Square. It's 3.5%. You will go to Madison Square, like 0.7, like 7%. You will go to the Herald Square. So, but how this Hoff model can define the probability? Let's move to here. Like this weight value, destination weight, really can control the probability. So, for example, like let's say this weight can represent the size of each square. So we assume that larger size of squares can absorb more people, like more attractive for people. So my observe, I'm in this location cafe here, and I bought a coffee I bought a coffee and then I want to go somewhere to have a coffee in a union square, in any squares. So, but I want to go somewhere nearby, but also larger space. So this weight can be the size of part. So if I can say if all the it should be some number. So if I say the 4 squares are having the same size, so we will see what happened here. So they are all same weight, 100. So we assume that the 4 squares are having same size, which means the same weight. So what happened here? Of course, if I have option, I will take the closest one, right? And also I can define the walking radius. I don't want to walk more than 4,700 feet. So within this walking range, I have 3 options. But all the size of squares are same. So I will take the shortest path, right? Because all the weights are same. So I just I need to have 2 conditions: the larger size, shorter distance. That is the rule to decide my destination. But the size of squares are all same. So the shorter distance can decide my option. So the shorter distance location will have a higher probability. So as a result, showing clearly showing the result very well. But here is the okay, head order square. So let's say the head order square, we increase it like 500. So let's see what happened here. So my probability changed, right? Even though I'm here and the closer square is here, union square, but this weight value increased like 5 times than the others. The probability increased a lot, right? So this is the Hoff model concept, like distance and the let's say attractiveness, which is the destination weight, really define the probability range. And also we can define the working range as well here, right? So this is the Hoff model. We uploaded all these example files, so you play with it, change the number, maybe you create your own hypothesis, or maybe you can also build your urban data, and then you can also bring here and you can play with it. And then the last one is very fun part. I just prepare it for architect. So this is Manhattan. We are still looking at Manhattan Island, right? So I choose one building here. Where is it? I think it's somewhere near the, yeah, here. I choose this building. Floor plan. I just very, yeah, abstractly, I just draw it, you know. So by using the between needs analysis, because between needs analysis reflect the realistic food flows, right, in a spatial network. So if you are architect and you want to analyze the building circulation, evacuation plan, if you know about the realistic the pedestrian flows within the network, you can design the evacuation plan or building circulation design as well, right? So just scale down from urban to building scale, and the logic is just exactly same. So instead of urban network, using urban network, we use the building indoor network, let's say. And then this is the, I just generate the numbers, the points. I can assume that maybe the room occupancy or like whatever, you can design it, like, or maybe you can say like number of people in the building. Also, you can say as an origin. And the destination is of course the exit. But this is the second floor. I just want to show you the just one floor plan first. So the result showing that the point is so small. So result showing that, yeah, I will just, this one is too small. And so yeah, it's okay. So this is a network on a second floor, and this is there is a stairs actually. I think there is a stairs. Here is a exit, because here is the stairs, so people should take the stairs like here. Here is the exit. So here showing the between is index value, the which represent the color code, and this is literally showing the visit number for each edge. So you can also understand like how many people or how many kind of origins pass by this edge. So you can also very quickly examine the flow plan, circulation, or design the evacuation plan as well. And let's move to the multiple floors. So this is
I think your Rhino file lose.
I think the file didn't really embedded in this component. Yeah, I will upload again. Sorry about that. I have to double check. So but the concept is same, but
otherwise, could you quickly open the Rhino file? Then everything gonna be connected to each other.
Yeah, maybe I will do that.
If you can.
I have to check. So, but basically the concept is pretty much the same, just exactly the same. But you can see the multiple floors, kind of.
She's in New York, Boston, so I think the time is 1 a.m., right? So I feel like she's become.
Yeah, I'm getting tired.
What's up? Yeah, you can make it.
It's the last exercise, so my part is almost done. And
Great.
after me, NJ will take over and he will take care of you guys. So. And if you have any questions, like just leave it on chat or or if you have any like ideas like how to use this tool, maybe you can share it as well and we can discuss about it.
I can see other people's face. They are like a little bit frustrated.
Oh, really? Oh my God. Like this is very basic version.
Bear with us. We can make it happen throughout the 2 weeks.
Yeah, but like I think if once you just set up, bring your own research question and then just try with it, I think you will understand very easily. No, so